All right, everyone. In this video, we're going to go through the rest of the resonance structure and resonance section pages, beginning on page 10. Looking at this example here, we're tasked with drawing the remaining contributors. Looking at the reference structure that we're beginning with, we have an overall negative charge, and what we want to do is move that negative into the adjacent pi system. So initially, I'll make a pi bond and break a pi bond. That blue arrow push would get us here, where we've made a pi bond. That's what the first arrow is communicating, and then we break the adjacent pi bond, charging that carbon negatively. This oxygen still has two lone pairs, and the C double bond O is still intact. All right. Now, because that negative is adjacent to the C double bond O pi system, I can make a pi bond and then break the adjacent C double bond O. The first arrow is showing a pi bond forming here between those carbons, and then as that pi bond is forming, we break the carbon-oxygen pi bond, delocalizing the pi density onto the oxygen atom, and that would charge the oxygen negatively. And if we had to say which one of these three is the most stable, I would say the far right contributor is the most stable, given that we have an oxygen of negative charge, and the other ones, we had carbon of negative charge. Oxygen being more electronegative would balance that better. Now, we knew exactly how we needed to push arrows because we were overall negative. Push it into the pi system, two arrows are required to go from one contributor to the next. Now, another problem type that you could potentially see is you might be given a structure, and you're asked then to draw the most stable resonance structure. So you're not necessarily asked to draw all contributors, but you'll draw the most stable. Now, in this example, we have a positive and a negative, so we'd want to move the negative towards the positive. I provided a template structure here as workspace. Let's just say we did an initial arrow push here. Make a pi bond, break a pi bond. I make a pi bond there, and that would charge this carbon negatively. Carbon-nitrogen pi bond is still intact. I would say that's not much more stable than the original structure, so I'm going to continue to push. I could then visualize making a pi bond and then breaking that pi bond. And I'm noticing that the arrow is terminating on the nitrogen. That means that as a result of that arrow push, we would have neutrality for the structure. First arrow is showing the formation of the carbon-carbon pi bond. Second arrow is showing that the nitrogen-carbon pi bond is breaking, and I'm neutralizing the positive and the negative. That would be the most stable resonance structure, and that's the one that you would need to draw. Now, if it helps in this type of problem, you can draw other contributors, as we did here, kind of visualizing the workspace, but ultimately make sure your answer is the most stable resonance structure, if that's what you're asked to draw. All right, moving on to the next example, we're just going to draw the next two resonance structures. All right, we have a positive and a negative. Let's move the negative towards the positive. I'm going to take that lone pair from the sulfur, make a pi bond, and then break the adjacent pi bond. Sulfur pi bonds to the carbon. Sulfur is now neutral, and I break the adjacent carbon-carbon pi bond, leaving that carbon negative. And the nitrogen at that point is still pi bonded to the carbon and positive. Now that the carbon that's negative is adjacent to the carbon-nitrogen pi bond, I can make a pi bond here and break the carbon-nitrogen pi bond. Sulfur, tracking on the far right, is staying the same. First arrow is showing the formation of this carbon-carbon pi bond. Second arrow is showing that the carbon-nitrogen pi bond is breaking, and the lone pair is left on the nitrogen atom, giving it neutrality, given that the arrow terminated on the nitrogen. All right. Excellent. Excellent. And the overall most stable would be this structure here. That would be the most stable. And then the second most stable would probably be the one where the sulfur is negative. Sulfur would balance that negative better than the carbon because sulfur is larger. Second most stable. And then the least stable would be the one with the carbon negative. Okay. But certainly full octet and neutral would be the most stable, far right structure. Moving on to the next page, page 11. The question is saying, for each of the resonance contributor pairs, indicate which is more stable, okay, which is lower energy. And notice that formal charges have been intentionally omitted. Any relevant lone pairs are present. So looking at the first pairing with you, we're going to have to track formal charge, which have been omitted. The carbon here is negative, and the nitrogen appears to be positive. In the right structure, it appears that every atom is neutral. Tracking with you, how we would go from A to B is we would take the lone pair, make a pi bond, and then break the adjacent pi bond, and that neutralizes the charges. Both of those structures are full octet, but full octet neutral would be more stable than full octet charged. B is the more stable contributor. Full octet neutral is more stable than full octet and charged. Not too bad. Looking at the right comparison, in the left structure, it appears that the oxygen is charged negatively, and in the right structure, it appears that the carbon is charged negatively. To go from A to B, arrow pushing wise, we might track here that the oxygen is making a pi bond to the adjacent carbon, and we break the carbon-carbon pi bond, leaving that carbon negative. Each of the structures are full octet. So we move on to charge accommodation. We're looking at O minus versus C minus. The oxygen is more electronegative. Therefore, A should be more stable than B. Oxygen is more electronegative. All right, just another example format you might see. Be sure to read the prompt and see if formal charges have been intentionally omitted. It's not uncommon for professors to do that. All right, and for the last example, here we have a larger structure, and we're going to count the total number of delocalizable pairs. Now, in an earlier video, we said that delocalizable pairs could be electrons in conjugated systems, alternating double and single bonds, where we'd count each pi bond that is conjugated as a pair. And then we could also count lone pair atoms adjacent to pi systems that are visually singly bonded. For example, this nitrogen can delocalize into that pi system, so I'd count that as one pair. And then each of those pi bonds I'd also count because they could resonate. And that lone pair atom, remember, could be adjacent to a benzene ring or a C double bond O or an alkene pi bond. So tracking with you, on the left side of the structure, that oxygen cannot delocalize any lone pairs because it's not attached to a pi system. So I'm not counting those. This nitrogen here is visually singly bonded and adjacent to the pi system, so it could resonate in. I'll count one pair for that pair there. Then I'd count a second, a third, and a fourth. Those pi bonds are conjugated with one another, and naturally as the nitrogen resonates in, we delocalize the pi bonds in the benzene ring. Looking at this nitrogen atom, it's not only adjacent to the benzene pi system, but also to the C double bond O. So I'll count that as a fifth pair. And if we imagine it resonating over the C double bond O, then the pi electrons in that double bond could be counted. But I cannot count the lone pairs on the oxygen atom because they would be existing in hybridized orbitals. The oxygen atom here is adjacent to the carbon-oxygen pi system, so it could delocalize one of its lone pairs. I'm only going to count one of the lone pairs on that oxygen atom. I would not count both. One would be in the p orbital, the one that we've counted as 7, and the other would be in a hybridized orbital. So if your lone pair atom is adjacent to a pi system and there's two lone pairs, count only one of those. Then on the far right side of the structure, looks like the nitrogen is visually singly bonded and adjacent to that pi system. I can make a pi bond, break a pi bond, so I'll count 8 and 9 for the pi bond. So a total of 9 delocalizable pairs. 9 delocalizable pairs, or we could say there's a total of 18 delocalizable pi electrons total. All right, I'm going to count those one more time for you because I think this is kind of a tricky problem type. On the far left, I'm not counting the lone pairs on the oxygen because it's not adjacent to a pi system. It has no resonance. The nitrogen is adjacent to this pi system, so I can count that lone pair as 1. I can then count each of the pi bonds in the benzene ring given the conjugation. This nitrogen can resonate into either pi system, so I'd count that as a 5th. I'll count this pi bond here as a 6th because that could resonate as a result of the nitrogen resonating or as a result of the oxygen resonating. Therefore, I'll count one of the lone pairs on the oxygen as being delocalizable. Oops, that would be 7. And then on the right side, I've got the nitrogen capable of delocalizing into that pi system. So I'll count 8 and then 9 for the pi bond itself. But again, we are not counting the lone pairs on the C double bond O oxygen atoms because those would be in hybridized orbitals. 9 delocalizable pairs, total of 18 delocalizable pi electrons if you're counting them individually. All right, so that concludes our coverage of resonance. I would definitely say that the examples that we've gone through are exam caliber examples. Be prepared to draw resonance structures, to gauge resonance structure stability, or to count delocalizable pairs of electrons.